So thank you very much. So I'm Pierre Moreau, I'm research engineer for plastic energy. So I'm going to talk first of plastic energy, who we are, the catalyst solution we develop. How did we improve the performance of that catalyst? How did we model the reactor at full scale? And we are going to propose a reaction mechanism for the first time ever, and then conclude and then talk about our future work. So first, plastic energy, who we are. So Plastic Energy is a global recycling technology company headquartered in London, so not too far from Sample. We've two commercial recycling plants in Spain, so one in Almeria, one in Seville, that have been operating for the past 7 years. So our team of technologies have around 16-year combined experience in developing a unique patented tag process. So that process converts plastic that would otherwise go into landfill, into the ocean, or be incinerated, into tackle, which is a feedstock that can be used to actually create virgin-grade plastic. And we are the only global company that has successfully and consistently produced enough feedstock or tackle to enable the conversion back into plastic. So I think everybody is aware of the plastic crisis, but just to give you some figures, so there's 1.8 billion tons of greenhouse gases that are produced every year due to the plastic life cycle, which is 3.4% of the total emission. Every year, there is 390 million tons of plastic that are produced globally. Of these 390 million, 22 million link into the environment or into the ocean every year. And overall, so there's only 9%, so less than 10% of the plastic waste that is recycled. 50% is landfilled, 22% is mismanaged, and 90% incinerated. So however, there's some hope. So there's an increased momentum to tackle the plastic waste. There's environmental and societal pressure. There's some trade restriction of plastic waste, and there's policy and voluntary commitment from different major companies. So why chemical recycling? So first, we can increase the recycling rate, so divert what is going into landfill or leaking into the ocean. We can increase the virgin quality of what is recycled, so we're able to produce food-grade recycled content. We have got also support sustainability goals, so reduce the dependency on fossil fuel and help the brand to achieve their recycle target. So what does plastic energy bring to the market? So until now, you are basically, sorry, that one, yes, you are the plastic production plant, and then either it was non-recyclable, so going to incineration or leaking into the environment, or you got a mechanical recycling loop, so you go to a mechanical recycling plant and then go back to the plastic plant, use bios, trash again, then you create a loop, and so on and so on. However, not all plastic can be mechanically recycling. So a fair part of the plastic is going then to the tag plant, where it's converted into an oil or tag oil that then can be used to produce more olefin that can be used to produce more polymer. And then you create what we call a chemical recycling loop. And that can go on like that. So Plastic Energy, who we are, so a global leader in chemical recycling. We got a patented technology. We've been developing that process over the past decade. We got very strong operational experience with two operational plants that have been operating for the last 7 years. And we demonstrated we're able to make plastic-to-plastic process with our product commercialized on the European market. And we got a global partnership with major players worldwide. So what is our mission? So it's basically first reduce pollution. So improve waste management by diverting plastic from landfill or incineration, creating a circular economy and creating a plastic loop, increase the recycling content of what has been produced, including food-grade plastic, so higher quality, reduce the oil dependency of the country we work with, so reduce the fossil oil consumption, and boost local economy and creating jobs. So what is our feedstock? So our feedstock, you can see here, it is basically real end-of-life plastic. It is dirty thing. It is not virgin plastic. And yep, okay. And it is basically mainly LDP, HDP, PP, PS, all end of life. What we can process still, but in lower quantity, is PET, PVC, EPS category 7. What are we producing? So we're producing an oil, you can see here, that we call tech oil. And that tech oil then can be taken by petrochemical company, fed into their steam cracker to produce some more olefin that then are used to produce some more polymer, some circular polymer. So here is a very simplified schematic of the plant. So we have basically the plastic coming, then it is melted. Then it is going to a reactor at high temperature here. Then the plastic crack and basically form a vapor that then go through a contactor that is a bit like a distillation column. Then through condensation, where the gas and the liquid are separated. So the liquid go to storage and offloading. And the gas is going to basically heat up the reactor. So what is the catalyst solution we developed? So first, just a reminder. So when we use a catalyst, we decrease the activation energy, open another reaction pathway. In the past, during my career, generally speaking, when you don't use a catalyst, you don't see any product. So I've been working for a very long time on Fischer-Tropsch, and that was the case. Here in the slide, I'm going to show you, if you don't use a catalyst, you still have a conversion since you still do the thermal treatment. So I just wanted to point that out first before going to the next slide. Then what type of catalyst we've been using? So we've been using zeolite. We've been especially using ZSM5 zeolite. That is basically an amine silicate zeolite belonging to the pentacyl family of zeolite. It is characterized by the acid size, silicate to amine ratio. There are some internal pore and external surface. There is a porosity with micropore and mesopore, and different acid number, different also by their strengths. It is largely used industrially for different reactions like carbon-carbon bond cracking, isomerization, dealkylation. It is interesting for us, it produces at ton scale every year. And so this material has consequently a lot of potential for catalyzing end-of-life plastic pyrolysis. So how did we start? So we started simply with 5 commercial zeolites that I'm sure a lot of the lab in the UK have around, which are basically the 5 ZSM5 you found on the website from Zeolite International. They differ mainly by their silica amine ratio from 23 to 280. So we tested that at a very small scale first on our micropilot reactor, which is basically equipped with a 300 milliliter reactor. The ZSM5 were calcined first in air at 500 degrees C, sieve between 125 and 250 micron. And there was basically mixed with plastic polymer mix at 0.5% weight. And the polymer mix is basically a mix of LDP, HDP, PP, PS, PVC. And this represents what we get in our feedstock. The reactor was obviously purged overnight with nitrogen to remove any presence of oxygen. And then we do the test for 2 hours at high temperature. And what do we observe? So to our great surprise, we saw that the most acidic zeolites, so ZSM5, 23, and 30, are actually the lowest activity. And even if we compare to the thermal, it doesn't show more activity. So it's basically showing no catalyst activity. On the contrary, the ZSM5, 50, and 80 shows the best activity and almost fully converted the batch. Then the ZSM5, 280, which is the less acidic one, is basically showing lower activity. So to our great surprise, the air silica to amine ratio is 50 for activity and selectivity to tech oil. So at the time, but I will come back to that later in the presentation, we had the hypothesis that a low silica to amine ratio, we got fast coking that completely deactivates the zeolite. And high silica to amine ratio, we got less acid site, which basically reduce the activity of the catalyst. So I always come back to that slide to try to understand what is happening. So 4 circles of catalysis. First, you synthesize the material, then you characterize it. Then you test it on your micropilot, then you model it on doing some kinetic modeling, and then at the center you get what is called knowledge. So how did we start our journey to understanding the results? So first, I used a software that is called GMP software. That is a statistical software that is very good at when you got different results, trying to relate the results to the physico-chemical property of the zeolite. So I've been putting in the software a lot of different parameters, acidity, silicate to mineral ratio, anything I could find. But basically, the two parameters that work the best were actually mesoporous volume and activity, so, and external surface area. And that correlates quite well with activity. And what does it tell us? That basically the zeolite with the highest mesoporous volume shows the highest activity. This suggests, so consequently, the pyrolysis reaction happened by pore move catalysis. So this gives us directly a pathway on how to improve the performance of the zeolite by basically increasing the external surface area or the mesoporous volume by doing some desilication. So how did we get on to that? So I've been simply using a recipe from the literature, doing free desilication, a different concentration of sodium hydroxide, 80 degrees C, 500 RPM for 30 minutes. Then I did free exchange with ammonium nitrate, 1 molar solution, calcination 550 for hours. The SN5 is pelletized, crushed, and sieved between 125 to 50 micron. And what do we observe? So for all treatment, basically the mesoporous volume is significantly higher, so between 1.7 to 2.1. At the same time, the microporous volume is reducing, so this is expecting, so you can have blocking by silicates. Then we've been trying to understand what was the impact on the reaction rate of the reaction. So for this, we did 3 TJ measurements at 5, 10, and 20 degrees C, trying to determine the 3 parameters of the kinetic equation that are the pre-expansion factor, activation energy, order of reaction. We use a sequential method. So first, we use systematically the Kissinger method to determine the activation energy and the pre-exponential factor, Codd transfer method to determine the order of reaction. It was always the first order when the catalyst was used, and then we did a final optimization to minimize the error using the Excel solver. And what do we observe when we compare the parent zeolite with the free desilicated? So as I said before, it's all first order, which is expected, and then activation energy didn't change too much, to be honest, but the pre-expansion factor changed a lot. So we got even a ratio of almost 100 between desilicated 1 zeolite and the SN550. So this shows that we haven't changed fundamentally the mechanism of reaction, but what we change is really the way the reactants are actually diffusing much quicker to the active site of the zeolite. Then we try to understand, to compare those results with the thermal case, which is basically no catalyst. Then we've been calculating the rate of reaction every time that is the initial rate of reaction, so concentration of LDP of 1. And then we've been normalizing the results first to the thermal case, which is basically no catalyst. And as you can see, whatever zeolite you use, even the parent zeolite is significantly more active than the thermal case. Then in the third column, we normalize compared to the parent zeolite. Here we see also there is an improvement. And what is interesting is that the improvement is bigger as the intensity of the treatment is increasing. So all of that is leading us to say that basically the reaction happens mainly by pore move and kilocatalysis. So this was introduced mainly at the beginning of the year 2000 by Professor Johan Mertens with hydroisomerization of an alkane. And it's been showing that basically the molecules are mainly reacting at the entrance of the pore or on the external surface. And then we didn't stop there. So we tried to model the process at full scale, so at the scale of the plant in Spain. So how did we get on that? So we use another software that is called Aspen Plus Dynamics. So we had to basically tweak the software. So it was not especially designed for our plants. So there's been a lot of add-on onto that, onto the normal software. We have input different data, so the kinetic equation, enthalpy of reaction, polymer property, polymer melt properties, product distribution, reactor geometry, dimension. And then you can get a lot of output data, like the batch time, the reactor polymer melt field level at mass, the flow rate of reactor vapor, actual reactor temperature and pressure, and the conversion. So we've been trying to compare three cases. So a case, the thermal case with no ZSM5. So we've been normalizing all the results to that case. The 1% weight ZSM5 loading and the 10% weight ZSM loading. So what to observe? So as the quantity of zeolite tested increase, we see that basically the batch time is reducing, which is very good for us, and then we can increase the throughput of the plant. At the same time, as expected, the maximum field level of polymer melt in the reactor reduced, thermal divided by 2 for the 10% case. Obviously, the flow rate of reactor vapor increase, and this is actually all right. See, it's still within the maximum allowable flow rate through the contactor. So we didn't stop there. We tried to see, okay, what happens if we double the flow rate of end-of-life plastic coming into the reactor? What happens? And in that case, that's interesting. So for normal feed rate, we get an improvement of 2.4, which is already very big, and we're very, very pleased with. But then if we double the feed rate, it's increased to 3.3, which is even more interesting. So this is significant. That shows for the plant that with thermal pyrolysis, the reaction rate is really the limiting factor. Whereas with the catalytic pyrolysis, then the feeding rate becomes a limiting factor. So from now on, we try in parallel also, in parallel all the scale-up work, etc. Try to understand what is the reaction mechanism, what is happening exactly. So I have to say that the first time I show these results. Okay, so first slide on that, reaction startup. There's been perhaps a lot of discussion on how the reaction is starting up, if it's starting catalytically or if it's starting in a thermal way. You will see we have an opinion on that. So here I showed just an example I was able to show. So basically we did 2 TGA, so one virgin LDP, 20 milligram, another one with virgin LDP and 10% ZSM5. So 20 milligram LDP, 2 milligram ZSM550. As you can see, so here we show the percentage mass versus the temperature. Basically, the reaction initiating a much lower temperature for the catalytic case compared to the thermal case. I have to say this is true at any scale we've tested so far. So for example, on our micropilot, we follow the gas and tackle production. And I can tell you that there is roughly 50 degrees C difference between the thermal case and the catalytic case. So it is really substantial. And for me, beyond doubt. Also, another important parameter is that whatever also, at any scale we do the reaction, gas is always produced first. You will see that has an importance for the rest. And that gas, so we did some online GC analysis, is very olefin rich. It's especially rich in ethylene and propylene, which is obviously interesting for us. But those molecules are highly reactive, even just by themselves, and even more reactive if you add the zeolite. So actually, so what is happening? So we've been with our partner at Poitiers doing some experiment where we fed actually just ethylene, so no polymer, but just ethylene, to the same 5 ZSM5 from the rational. So we use 300 milligram every time, shift to between 200 and 400 micron with a fixed bed reactor, 7 degrees C, at room pressure, and we purge the reactor overnight with nitrogen, and then start the ethylene, nitrogen ethylene to ratio volume to volume 20. So this is called, by the way, the alpha test. And what do we see? So the most acidic zeolite, which is in red here, is actually dropping the activity is dropping very fast. So there is a very quick deactivation. Then the second least acidic is actually dropping fast, a little bit slower. Then the 50 to 1. Then the 80 to 1 show lower initial activity and then the activation. And then the least acidic is show almost no activity. Also, zeolite show coke deposit except the 280 to 1. And once again, the DSM-550 seems to be the best compromise between activity, initial activity, and deactivation. So this leads us to think that the molofin basically reacts initially when we do the reaction with polymer, and that will basically condition the zeolite for the rest of its life. Then we've been looking at what is happening post-reaction. So we've been doing a lot of characterization post-reaction. So we've been doing the reaction for 16 hours for the same 5 zeolites. So we did 16 hours to be sure it was fully converted and we were able to unload the catalyst. Been using 2 instruments, a micromeritics reflex instrument to measure porosity, and then a CHNS elemental analysis from Elementar. So what do we see? So whatever zeolite you use, there is always porosity loss. So that is in gray here. So here is percentage loss versus the different zeolite. In yellow is the microporosity. So you see the microporosity loss is basically increasing as you increase the acidity of the zeolite, to the point that the most acidic has completely lost its microporosity. On the contrary, the biggest mesoporosity loss is actually with the 280 to 1 zeolite. And also, so it's not displayed here, but we did the percentage carbon at the end measurement. And basically the percentage carbon is increasing as the zeolite is becoming more and more acidic. Which leads us to say that the coke deposit is the main reason for the activation. So here I'm not showing the results, basically it's end-of-life plastic, but it's still true with end-of-life plastic. And this is despite there is a lot of poison within that end-of-life plastic. So what was also very interesting, we did that same experiment for only 2 hours, since we wanted to compare primarily the different activity of the zeolite. But actually, 2 of the zeolite has fully converted the batch in 2 hours, so they were very active. That was DSM-550 and 80. So we've been doing the same measurement. And what we observed is that for DSM-50, the porosity is almost completely lost, the microporosity is completely lost, the mesoporosity is almost fully lost. But that zeolite is still active, since we are still able to reuse it several times. But then we compare the result with the 16 hours. What we observe is that a large part of the mesoporosity and the microporosity is recovered, which shows that the zeolite is still active and can actually, when there's no more LDP, can actually crack the coke. Then some 80 is not too much affected by pore blockage. And that doesn't change too much after 16 hours. So also an important parameter. So we did, with our partner from the Catalysis Hub, some corrugated Raman spectroscopy. So we've been collected different Raman spectra at different temperature with a mixture of LDP zeolite 1 to 3. And then there was a mass spectrometer on the outlet. And we are able to do mass spectrometry, so basically to determine the content of the product. So what we saw is that basically we have a buildup of carbon, double bond carbon-carbon containing hydrocarbon on the zeolite surface as the plastic starts to crack. So we see that basically with the blue dotted line, the LDP element vibration weakens. And then we got a buildup of aromatic, monocyclic aromatics on the surface. So we can see actually those aromatics being produced. But the mass spectrometry is that very important, show us that basically we are getting the same product that we get in our micropilot and pilot. So mainly lathycane and alkene, heavier alkene, and aromatic products. And finally, we've been looking, so what is the composition of the coke post-reaction when we recover the catalyst? So for this, we've been using a method developed by my PhD supervisor, Patrick Magnew, at Poitiers University, where we dissolve the coke zeolite in a concentrated fluoric acid. Then we do an extraction with dichloromethane. And then we inject that for the soluble part onto the GCMS. And what are we finding? So finding different molecules of naphthalene, substituted mono D3 naphthalene, fluorine, phenanthrene, anthracene, dimethylpyrene. And you can see you can grow the cycle of aromatic. You can go to very, very large molecule. Here, the only limit is how much space there is around the molecule and basically the supply of olefin, of ethylene and propylene. Finally, looking at aromatics. So here, still on our micropilot at 400, been reusing the same zeolite over and over and over again. And something that came quite striking was that the yield of aromatic versus the run number. So as you can see, it's produced quite high level initially, but then it is decreasing to the point that after 6 reuse, we don't see any more aromatics. And also, we were managed to fit an equation with a very good correlation factor of 99.52%. So that shows that the aromatics are produced certainly initially within the pore. We know the pore are getting blocked, so the microporosity is getting blocked, up to the point that no more aromatics are produced. So let's get on with the reaction mechanism. So I divided that into different stages. And here we've got a framework, so the SM5 framework that is virgin, so there is nothing within initially. And there is an LDP molecule here. I just remind you that LDP is not force linear, so it can be branched. So what happened initially? So from our different experimental evidence, we think that the LDP is reacting on the external surface initially, or in the pore mouth, as was shown here by Johan Mertens, and start to form some gas. That gas is very rich in ethylene and propylene. So this is the step 1, startup. Then we got into step 2, that's called conditioning, where basically LDP is still there. So you still have some LDP in the reactor, but you have formed some gas. You start to form some tackle after around 20 minutes. And that gas is very rich in ethylene and propylene. Now that ethylene and propylene can, contrary to the LDP, can diffuse within the pore of the zeolite. And that ethylene and propylene is going to do some reaction within the pore of the zeolite. And what is going to do? Dimerization, oligomerization, etc., repolymerization, etc. So you start to form some gas, some tackle, including some aromatic. And the last reaction you form is basically you're producing coke. So you're producing some polyaromatic molecule that start to form either very close to the external surface or really deep within the SM5. Then we go to state 3, which I call steady state. So at stage, the coke is growing. The coke is always growing so long there's feedstock and space to grow. We still have got some LDP that basically is converted on the external surface. Now, it cannot go inside. So basically, the microporosity is fully blocked by the coke molecule. So this space here is becoming completely unavailable to the reaction. And then it does react, and then it does still form some gas and some tackle and some olefin. That reaction here is not forming anymore. So we don't see anymore the aromatic. And that goes on until you run out of LDP. Then when you run out of LDP, so what is happening? So I call that cooking. So you just have your zeolite and some coke molecule. The zeolite is still active. If you put more LDP, that will convert. But given that there's no LDP and there's just coke molecule, it starts to convert the coke molecule into gas. So we don't see any tackle, it's only gas at that stage, and that gas is still very rich in ethylene and propylene. Then what you can do, you stop your reactor. You can actually do an oxidative regeneration at high temperature of your zeolite. So what we observe when we do the oxidative regeneration, so of course, before regeneration, zeolite is black. After, it looks, of course, very white. It's not as white as the fresh zeolite. I would say it's more cream color. And when we do CHNS analysis, you see a bit of carbon. So we think that carbon is really deep inside the molecule, since when we do the reaction again, honestly, from a reaction rate point of view, we don't see the difference at all. Then if you put more LDP, but you do the same. You react on the external surface or in the pore mouth. Then you form some more gas, some more tackle, some more olefins that can diffuse inside. You form some more coke that can produce some more gas, some more tackle, some more aromatic. And then you go through the cycle, and you can do several cycles of reaction, regeneration, up to the point that the zeolite is basically not active enough to be interesting. So to conclude on that slide, yeah, there's a minority of coke that is refractory to regeneration, but it is not a problem for us because we get the same activities initially. Then I try to think, but actually, so if there's in the literature any other example of such reaction with medium-pore zeolite, which the DSM-5 is, with hydrocarbon. So there's two examples, but there might be more. So there is Johan Mertens study Q11, study hydrogenation with theta-1 zeolite, where he's been showing that basically there was a mechanism of reaction by absorption of the external surface of the crystallite, and then got the reaction without the pore move on the external surface. And then the second example is basically my PhD that I did between 2002 and 2005 with AFPN. So I've been studying acid benzene hydrogenation. The idea was to form xylene to after form terephthalic acid, so to form PET bottle. So they wanted to maximize the xylene from the C8 aromatic cut in the refineries. And they found a zeolite that was called EU1 zeolite that has basically some interesting properties. So what we observed, it was deactivating very, very quickly initially. To show up. Yeah, so the open symbol of the initial quick deactivation, and then stabilization. So initially you've got reaction both inside the micropore on the external surface, and you got coking to the point you fully block the microporosity, and then you got only reaction on the external surface. So you form more, you increase your selectivity in isomerization, which is actually the product you want. So that was a very interesting process. So that is certainly not limited to that. But that was the two main examples I could think of. So conclusion, the future work. So I managed to show that the 25-to-1 zeolite is the most interesting one. Desilication for us is an efficient and economic method to improve significantly the rate of reaction, the throughput for the plant. We think that the reaction happened mainly by pore move and kilo catalysis. The reactor model has confirmed the results we're getting from the kinetic rate. So we can improve the throughput by 2.4 and for standard feed rate, 3.3 for double feed rate. And this is a very good news. I mean, we can process more end-of-life plastic potentially. Shows that the reaction limited by reaction rate for thermal pyrolysis and feeding rate for catalytic pyrolysis. The final point, so yeah, there's a lot of optimization of the plant that will need to be done to accommodate the catalyst, obviously. And I have to say also, so there is, of course, what was the purpose of the project, which was to increase the throughput of the plant. I have to say there's a lot of detailed advantage of using catalyst compared to doing thermal pyrolysis. I'm not going to get into the details. It's not only the increasing the throughput. So future work. So The ZN5 formulation had been actually scaled up at our third party this year to 20 kilograms. It was successful. Characterization testing on the micropilot came back positive. Once we'll have a slot that will be tested on our 30-liter pilot plant reactor with end-of-life plastic. And then if it's positive, we'll manufacture that to ton size of our third party, and then do a demonstration our plant in Spain for the deselected ZN5 zeolite. So all the people who have been helping me to put together the presentation and generate the results. So thank you, Emily, Daria, Abby, George, Alex, Andrew, David, Anthony at Loughborough and London, Poitiers University, Isabel and Leah for catalyst characterization and Koch analysis, Loughborough University, Sam, Sandy, and Simon for material synthesis and several advice, Catalyst Hub, Edma, and Andy Bill for catalyst synthesis, modification, catalyst characterization. Well, thank you, and I'm open to any question.
Thank you very much indeed. Yeah. Questions? Yes.
Yeah, thanks ever so much, and great to see the progress. So I heard you speak earlier this year. Many of your tests were done on a mixture of 3 olefins, so ethylene, propylene, styrene. What is your commercial target, and how sensitive is the process to different amounts of those 3 olefins?
So, I mean, there's been a lot of tests done. I mean, a lot, yeah. I mean, I say a decade, it's really a decade. I mean, they started perhaps the test on the pilot plant in Ireland in 2008, so to show you the scale of the work that has been done. So basically, that's what you found in your bin, basically. As I say, we try, can go back actually. So first, LDP is by far the main polymer that is produced worldwide. And then you find PP and PS. So I can't disclose too much about that because there's been a lot of IP linked to that. So if a customer come to us, we've got a guideline of like the feedstock needs to have no more than this polymer, no less than that, basically. And it's based on tests that we did doing different mix and seeing what happened. Can tell you there's been a lot of reactor blockage if you use certain polymer. There's been a lot of learning made. And that's what was interesting to have also this plant in Spain, is to be able to test different configuration. So, but basically our, as I say, so I don't know if you can go back quickly. No? Yeah. So basically LDP, HDP, PP, PS is what you find mainly. So the one we don't really convert is PET. So the one who is on this one is special. So it has oxygen, etc. If you do the thermal case. So this one we can process it, but we shouldn't excess. There's a maximum level we can tolerate in our plant.
Thanks, Pierre.
Thanks, Pierre. That's really interesting. And it's really impressive that you get a 3.3 times increase in throughput. That's Catalyst for you. The other thing that Catalysts do is they can change the selectivity. Do you see changes in?
So yeah, yeah. So there's a lot of talk about the literature and what is happening when you use catalyst versus. So I would say the selectivity depends on a lot of parameters. And so it will depend which catalyst you use first. So the good thing is that actually the deselected catalyst is more selective to liquid. Then that depends on the operating condition. So be careful. For the thermal catalysis, the optimum temperature is like 400. Currently, the catalyst is so active so that in order not to be at 100% with our micropilot, now we are 340. So that shows you 60 degrees, just huge. But to come back to your question, be careful. The gas is a product. The gas is actually very interesting. See, it's rich in ethylene propylene. composition doesn't change too much when you do the reaction. Once the reaction started, once you got that initial flash in gas, it's very consistent what you produce. And it is very rich in ethylene propylene, just what you want to make more polymer. So there will be two types of plants. So it will be the type of plant like Sevena, just by themselves. So those one who try to maximize the liquid, because the gas, well, you need to compress it after if you want to send it somewhere else. Liquid is much easier to just put into a tanker, and that's fine. But we got a plant like we got a plant in Netherlands, in Geleen, that will be directly linked to a steam cracker, and we are going to produce gas. So I mean, the obviously thing to do is to send that to the steam cracker directly. So it can be, I mean, the gas can be actually interesting if you're close to a petrochemical site. Since then, basically, what we get as gas is very close to what they get from what is the output of the steam cracking. So be careful, don't remember, you need to fill the whole chain. So there's the steam cracking, but then after, you don't, outside the steam cracking, you don't get a single flow of ethylene or propylene. It's all mixed. So then you're obliged to do a cryogenic distillation to separate the different olefins. So that is actually very interesting. So that is also a possibility. I saw the question around when we use zeolite, if we could maximize the gas, which is actually possible, but that's two different ways to drive the process.
Okay.
So I guess your process economics, you will be required, or you are required to regenerate the zeolite. So therefore, I guess the optimum operation may not be to run the zeolite all the way through to loss of activity. You may wish to regenerate it earlier than that. I guess you have thought about that. And I wondered if you thought about trying to recover any energy from the coke which you're forming in the process.
Good question. So let's start. Sorry, let's start. So yeah, think you pay for the zeolite. So I'm always in comparison with the thermal case. So we are doing techno-economic to show that actually, so the problem, you pay for the zeolite, so you're going to increase your OPEX. You need to show there is a significant increase compared to the thermal case, so that it is, so you still make a profit while paying the supplier. The supplier needs to make a profit also, so the whole chain needs to make a profit. What we observe is that, so we managed to make the zeolite very active, I have to say. So now we're getting very low in zeolite content. We won't go to 10%, I can tell you. There has been so much progress. These results are even a bit old, so we made some further progress since. So you're not obliged to use that much, to the point that would be the devil advocate. You could say you can get away without any regeneration. However, a company, we say we're all about circularity, etc. So we'll do regeneration. We try to use a third party. So I'm in contact with third party to do regeneration. So we'll do reuse up to the point. So the point, we won't go to the point where the zeolite is completely inactive. So you don't want to get to the point, to the thermal case. If the zeolite is completely inactive, that is a thermal case. So that is not interesting anymore. So you better send out for regeneration. So that is actually we started last year, the economic model, and it is very positive. I can't get into that because it's very secretive, but it is very positive. It is, yeah, I mean, we get a price range from the supplier at the autumn, and we're in a very good position.
Okay, I think we've run out of time. Thank you very much indeed, Pierre.
Thank you.